Oh, welcome guys. So in this short video, I want to introduce the quantum phase estimation. Okay, so this problem is already demonstrated clearly and easily in the Wikipedia, but I just want to make each step more clear and describe step by step. Okay, so the quantum phase estimation idea is that we have a U, right, a unitary and some state phi, some state psi, and let's assume that psi is easily prepared. So, however, you have a psi, right, and the unitary operator U act on psi will be exponential 2 pi I theta psi. So the theta is defined to be from 0 to 1. Okay, greater or equal to 0 and less than 1. And our task is to estimate psi. Also, so estimate theta angle. Okay, so just record that by definition, if you get u2j 2 to the j psi will be exponential 2 to the j theta phi psi, right? So this is just straightforward. So that's so this is the quantum circuit is defined to be start from all the zeros and you have a psi and let's say you use n. Okay, so you use n of 0 to prepare this. So your initial state is 0 to the power n psi, and then you act on Hadamard. So Hadamard act on all 0, right? Will give you this guy. Okay, then you use a lot of control gate. So that control u2 to the 0, control u2 to the 1, and up to control u2 to the n minus 1. So then you apply the so-called inverse quantum Fourier transform and do the measurement. Okay, let's say step by step. What's the results? Okay, so up to this stage. Okay. So let's say what is the quantum phase estimation to the n qubits? Okay, so this is your state, right? If you expand it, then the since you control u, right? So if so if for this one guy, right? If this is 1, then you will create exponential 2 pi I2 to the 0 to psi for the this one, and for this one, you will produce the okay. So let's say so all these steps are for the for this cu naught to u to the 2 to the 0. Okay, so let's see. So this guy will act on the n qubits, so it becomes this tensor with the rest, right? So this is 1 to n minus 1. So these are all the same, right? So you can write it as this, and for this one is this. Okay, so then you can expand it. You can pull out this side, right? Become this, and then become this. Right. So this is the results. The final result for after you use control U to the 0, then you will get this. So this is for the control U1, U to the 2 to the 1 and U to the 2 to the 2 and power, then your final result will be this one. Right, this is for n qubits, then you can go to the n minus 1. N qubit are n minus 1, so it's 2 to the 1, and the first one is 2 to n minus 1, so start from here. So it's cu 2 to n minus 2 to n minus 1. Okay, so these are all the states here. Okay, this guy. And then you can expand it. So if you expand it, you get 0, 0. And but it's easy to see that this is just exponential 2 pi I theta k. Okay. And the k is from 0 to 2 to n minus 1. 2 to the n minus 1, because this 0 and 1 will accumulate to from each basis from 0 to 2 to n to minus 1, and you get exponential 2 pi I theta k. Okay, then you start from here, and then you apply the inverse quantum Fourier transform. Okay, so just recall that the inverse quantum Fourier transform is that suppose you can write your x into xii, so it's x, and you can define y, and you can after Fourier transform you get some y, you get yk, and this yk to be 1 over square root of n x let's say xi omega I K N, right? And this is let's say I. This is I. And there's a minus sign if y is a inverse quantum Fourier transform. Okay, so start from here. This is your, and you use 2 to n. So this is omega n to the minus ik. You get this, and then apply on x, right? So this k quantum Fourier transform will become this. Follow this result, right? This capital N is the 2 to n. So you get this. And combine these two, you get this. Okay, so the rest is that the rest, if you go to, okay, so combine all of it, then this is your final state before you get a measurement up here. So now if you get a measurement, you can see one can just see the final proof. Who call me? Okay, so then you measure A, right, and X, and then you just take a square. Okay, so you get this. And it's easy to see that this delta is defined to be defined to be the error of this x minus a. So if you do it, so so that means you can get an approximation so that means you can so let's assume that theta can be written as like a or I should say theta divided 2 to n will be some integer. Okay, so suppose, right, so you can view this x theta divided by 2 to n will be sorry, what I'm writing about. 2 to n theta will be integer. Okay, so if 2 to n times theta is like a good approximate integer as an integer, then x is already an integer, right? So once you measure it, then you can get an approximation. You can approximate theta, right? And what approximate theta you get is that if you times 2 to n theta, and you will get the integer part. Okay, so that means if you take n to be large enough, then you can get a good approximation for this theta. So if n goes to infinity, then basically it's like you can expand theta as the digits, like as like a base 2 digits. So if you get large enough 2 to the n, then you can approximate theta into arbitrary error, right? Basically, the idea is that you just try to truncate. Okay, so after you do this, you measure. Okay, so it's like a wiki. If you measure this a, right, then you will get a good approximation for this data. So the idea is that you can measure n bits estimation of theta with high probabilities, but increasing the number of qubits by this one. Okay. So this idea is called quantum so-called quantum phase estimation. So it's basically very amazing that somebody give you this u psi equals to 2 pi I theta psi, and one can measure theta easily. Okay, so that's the proof. Okay, I think up to now we already introduced the Shor's algorithm and the quantum phase estimation and the quantum Fourier transform. So everything for like the standard quantum computing is already set. So I will close this playlist, for a while, and go through next interesting topic which I intended to do. Okay, I will see you guys in the next video. Be sure to subscribe to my channel. Thanks.